cover the problem night minimum moves on Algo Monster. So you'll see here that we have an infinitely large chessboard, and we have a knight from chess that is positioned at 0, 0. So we'll define it to be the 0th row and the 0th column. Knights in chess can move in 8 directions. You can see the kind of 8 directions that a knight can move to, marked as X's, assuming that the knight starts right here. So it's kind of these combinations of moving 2 steps in one direction and then 1 step in the perpendicular direction. So we can go 2 steps this way in 1, 2 steps this way in 1, 2 steps this way in 1, and you can kind of get the process. Now, we'll be given a destination coordinate given by an x and y, really a row and a column, and we have to figure out the minimum number of moves for our knight to start at 0, 0 and end up at this given position right here. Now, we've seen this before, but this matrix right here can kind of be visualized as a graph, and it really is a graph. The reason that we could have some clue of this is we want to determine the minimum number of moves, and we're starting at some position and ending at some position. This kind of sounds like we're saying, hey, we're finding the shortest path from some position, some start position, to some end position. So if we try to use that way of thinking about this problem, let's see if we can visualize this as a graph and then use our standard breadth first search shortest path algorithm. Well, if we have a graph here, what are our nodes? What makes the most sense is our nodes are probably going to be each of these kind of squares here on our chessboard. And to figure out what our edges are, we need to think about neighbors. Now, remember, neighbors are basically answering the question, from my current node, what is the set of other nodes that I can get to directly, just by taking one edge? So, remember, our nodes are just positions. So if I'm at this position, what other positions can I get to directly in one step? Well, I cannot get over here, for sure. I actually cannot get here, cannot get here, cannot get here. The only places I can go are these 8 directions. That's kind of the definition of how a knight operates on a chessboard. So, given some particular position specified by a row and column, we can enumerate its edges. We just have to find these 8 x's relative to the starting position. Then we have our positions defined as nodes, we have an idea of what our edges and neighbors are, and we're trying to figure out the minimum number of edges we need to take to start at 0, 0 and end up at x, y. In terms of the graph, we are starting at some node and we want to end at some node, and we're figuring out what are the minimum number of edges that we need to take to get from the start node to the end node. With this framing, this is a pretty classic BFS shortest path question. So we are going to simply execute a BFS where we start at the 0, 0 position and keep going until we hit our target position and count the number of edges that we took to get there. The way we'll do this is we will store some metadata in our queue. So for each node in our queue, which we're going to have a row and a column, which we need to uniquely identify that position. And we're also going to store a distance from start position, which just shows how far we've traveled. Because we'll have 3 pieces of information, I'm going to define a class for this, just because I think it makes things a little bit easier and cleaner, but this is personal preference and it's definitely not necessary. I think if you start getting 4 or more pieces of information, it might become more important, but for 3 I think is kind of optional. So we'll have our constructor, we'll have 3 properties, we'll take in the row and set the row, take in the call and set the call, and we'll have our distance from start position, which we set as well. Now we can start working on our core BFS logic right here. So we're going to create a queue. Now in Algo Monster, they do not have an actual queue built in for us. So we're going to use an array, but we're going to have to do something careful we're going to have to be careful when we're using an array. We'll see that in a moment. Now we want to push our start node here, but we should actually create that node. So we can say start node is going to be a new node. We know that we're starting at 0 and 0, and we know the distance, the number of moves we've made to get to 0, 0 is just 0. We haven't made any moves yet. And then simply we're going to push our start node onto the queue. Now sometimes here we'll create a visited set. Do we need to do that here? Well, we want to use a visited set when our graph can have cycles. because if we have cycles, then we can get stuck in infinite loops. Now, if I'm a knight and I start here, then I jump to this position, can I jump back to that position somehow? Well, yeah, I can literally just take the direct move to go from here back to here. In fact, we have an undirected graph. If you can go from A to B, then you can go from B to A. And this means that we definitely can have cycles, which means we must use a visited set. So let's create our set right here. All right, now we'll have our standard BFS loop. So we're going to say so long as our queue is not empty, we're going to do our standard 3 steps. So we'll have our remove node, our process node, our add neighbors. Now here, we are going to say node is going to be queue.shift. Now here's where we have to be careful. This really just takes an array and removes the first element. And this requires linear time, because all of the elements after the first element just get shifted backwards. So we want to make a note here. We'll say in practice, we should use a real queue class so that we can dequeue in O of 1 time instead of O of n time. The reason we're making this note is even if you explicitly state this to your interviewer, oftentimes the actual code you write is given to something like a hiring committee, and your interviewer may have not written down the fact that you discussed this and decided that using a queue as an array is okay for now. So you want the hiring committee to know that you legitimately understand that this queue is not the optimal implementation and that you know what you're doing as a developer. Now we'll also destructure out the properties that we want to have access to here. So we can grab these out. We'll do our process node step. I'm going to leave this and come back to it because that's kind of where the core thinking happens when we're doing a shortest path question. Now, let's see. We need to actually get our neighbors. Now, I'm going to defer to another function to do that for us. So we'll say get neighbors here, and we'll obviously need to know the current position. We'll leave that function's implementation up, so we're not going to do it right now. But I'm going to stub out the function right here just so that we don't forget to do it later. Okay, now for each one of our neighbors, what do we want to do? Well, we can, let's say our neighbors are going to be, each neighbor is going to be an array that contains a row and a call. So we'll grab our neighbor row and neighbor call from the neighbor like this using some array destructuring. Now, what do we want to do? Well, we want to check that we have some sort of valid combination, and as long as we have a valid neighbor, we want to put it on the queue. Now, we might think based on this picture that you want to check, what if we go out of bounds? But we're using an infinitely large chessboard, so there actually is no such thing as going out of bounds here. So we don't need to make this check. Now, we do need to check if we have already visited this node because of the cycle problem that we mentioned before. So what we'll do is we'll say if visited.has something, continue, just skip it. Now, what I'm going to do here is I am actually going to create our node first. So we're going to say neighbor node. It's going to be new node. We'll have the neighbor row, the neighbor call, and we'll have distance from sort position +1. Because we have now just made one extra move to get from node to neighbor node. So we have to add 1 here. Now, here I'm going to pass in my neighbor node, and then I'm going to have a getPositionString method on that class. And basically that's going to return a unique string that identifies a node based on its location, based on its row and call. We can actually just implement that right now. So we'll have a getPositionString. It's going to take in no arguments, and it's going to return a string. We'll use a template literal here. We can say this.row, comma, this.call. That way we can identify this node with a unique string. And if that string is already in our visited set, then we know we don't even need to add this guy to the queue. Otherwise, we'll go ahead and push the neighbor node onto the queue. And note that we want to push the node here because that's what we are using up here. We're using entire nodes and destructuring out various properties. All right, now we want to figure out our process node step. So the key thing with the process node step is we want to figure out when to finish. And how do we know that we have finished in our case? Well, the kind of goal of our shortest path algorithm here is find the given point, find x, y. So we can say, if our current position is x, y, then we know we're done. Now, I actually want to rename x and y because I don't think they're that descriptive. So we'll have target row and target call. That's what I'm going to name them. So we can say, if row is equal to target row and column is equal to target column, then we return the number of moves we made, which is just distance from start position. And we know the first time that we find target row, target call must be the minimum distance from start position. That comes from the fact that BFS goes level by level, which we've covered in the past. Now, the last thing we want to handle here is that we need to actually add the current node to our visited set. It doesn't actually matter in the case where we are returning, but for most of the cases, we will be grabbing out a node and we do not return. So we want to mark it as visited so that we don't ever visit it in the future. So we can say visited.add, and we'll add our current node.get position string. And we have to have those strings in the visited set here, because if we were to just use the actual node itself, that can get complicated with memory addresses. Sometimes two nodes will have the same contents, but they have different memory addresses, and then that gets confusing. So we want to make sure that we use strings here. Okay, now I believe we simply have to implement this getNeighbors function, and we should be good to go. So before we do this, I'm going to make our directions array. And here we want to specify each of these 8 directions. So we'll just be careful about how we do this. I'm going to start at this x and go clockwise. So this x moves 2 rows back and 1 column back. So that's going to be -2, -1. This x is 2 rows back, 1 column forward. So this is -2, 1. This one here goes 1 row back, 2 columns forward. So we have -1, 2. This one here goes 1 row forward, and then 2 columns forward. So we have 1, 2. Then this one goes 2 rows forward, 1 column forward. We have 2, 1. This one goes 2 rows forward, 1 column backwards. We have 2, -1. This one goes 1 row forward, 2 columns backwards. We have 1, -2. This last one right here goes 1 row backwards, and then 2 columns backwards. So we have -1, -2. Hopefully I got all those directions correct. If I did, then constructing our neighbors should work something like this. So we'll create our neighbors array and return it. In between, we'll iterate over every direction. So we'll say for each direction of directions. And then we want to grab out these 2 values, the -2 and then the -1 in this case. So we will say const, let's say row change, call chain equals direction. So that's all these are here, right? This -2 is just saying take whatever row we're at and move 2 rows back. This -1 is saying take whatever call we're at and move 1 call back. So this is our row change and our call change. Now we can say our neighbor row is just going to be row plus row change, and our neighbor call equals call plus call change. And we can simply say neighbors.push an array that contains neighbor row, comma, neighbor call. And so this is basically going to take the current row call and try making 1 move in all 8 of our directions. Let's confirm that we actually have 8. There's 4 here and 4 here. Yep, we'll make 1 move in each of our 8 directions, add those to our neighbors array, and then return those to be used here. All right, in that case, we can go ahead and run our tests and see if there's anything we're missing. All right, it looks like we passed these test cases. So that's all for this video, and thanks for watching.